Welcome back, students. In the last lecture, we derived the internal energy and the heat capacity based on quantum mechanics. Today, we will have a look at specifically entropy. We'll look at all of our other thermodynamic functions and also end on the equilibrium constant. So the focus for today is going to be entropy and equilibrium constant, but we will also cover our other parameters that we haven't talked about yet: enthalpy, Gibbs free energy, and Helmholtz free energy. So the learning goals for today are going to be the same as last time. We're going to be focusing on how we can explain the bulk thermodynamic properties based off of the quantum mechanical molecular partition function. And today we're going to go through entropy, enthalpy, Gibbs free energy, Helmholtz free energy, and equilibrium constant. So we are going to start with entropy. Now, what are we going to do with the entropy? So what is entropy? Entropy is typically described, especially in the high school gen chem, just learning chemistry context, as a tendency towards disorder. Why, right? Why does the universe tend towards disorder? The universe doesn't tend towards disorder because the universe is inherently chaotic, but simply because there are more disordered states than ordered states. So we'll go to the board here and think about an example. Consider this 5 by 5 grid as a volume that molecules could occupy. If we take this grid as a space that we could have things, we could have, say, 2 atoms in this space. We could have an atom here, we could have an atom here. What is the entropy of this arrangement? Well, the entropy is simply going to be the weight, right? And so we can calculate this. The weight of this system is equal to the total number of boxes, which in this case, our 5 by 5 grid gives us 25 boxes. And then what goes in the denominator? Well, it's just like a coin flips, right? What are the options? The options are filled or unfilled. How many filled boxes do we have? Well, if we have 2 atoms, we simply have 2 filled boxes. How many unfilled boxes do we have? Well, the rest of them, which is 23. So we can calculate the weight of this scenario with our simple coin flip calculation for weight. And if we do this calculation, we find that the weight of this arrangement with 25 boxes and 2 atoms is simply 1,500. Now, what if we were to form a molecule? Well, if we were to take our 2 atoms and form them into a molecule, our atoms now have to be connected. So we can have either one of these examples shown down here. Our atoms are connected into a molecule. In terms of order, right, 2 atoms are more disordered than 1 molecule. So the entropy, the order, has decreased as I make this molecule. Now, what happens to the weight? We can use the brute force method for this simple example to say, well, how many of my total 1,500 microstates have these 2 molecules or 2 atoms adjacent in 1 molecule? And we can simply find them all, right? We can move our molecule around in these boxes and count the total number of different options. And in doing so, this 1,500 is for the isolated atoms, and to have them be molecules, there is only 40 different states that has that outcome. So which of these states is more likely? Well, it's obviously the one in which there is the largest entropy. The more entropy, the more likely something is going to be. So the larger the weight, the more microstates, the more entropy something is. So you can think about this, right, to use, a bedroom as an example. There's way more ways to put all of your possessions disorderly throughout your bedroom, so they will tend to be disordered. There's only one or maybe a few right places for these objects to be, and so they're less likely to be in those spaces. This works for our houses and our bedrooms, and it also works for molecules as well. So we are just, the entropy increases, the disorder increases simply because that's the largest weight. And we already talked about this before using Boltzmann's definition of entropy. We brought this up a little bit way back when we talked about entropy earlier in the semester. Boltzmann says that the entropy is nothing more than Boltzmann's constant K times the natural log of the weight. This shows this relationship between entropy and weight. As weight increases, entropy increases. And we can note this as well when we talked about entropy. entropy was maximized at equilibrium, the weight is also maximized at equilibrium. So that suggests this relationship as well. But how can we actually, prove or derive this simple relationship, entropy being K natural log of W? We can start by considering an ensemble of particles and describing the ensemble energy. So the energy of an ensemble of particles, E, is equal to the sum of the energy levels for each individual unit of our ensemble, and then times A, the occupation number, however many units of the ensemble have that energy. And if we sum all of the energy levels for all of the different pieces of our ensemble, we'll get the total energy. We can evaluate the differential of this. And so what we're going to do is evaluate the differential of energy, connect that into entropy, and then we can remove the differential at the end. So we can say that dE, the change in energy, is equal to the sum over n of epsilon n dAn. And then using the product rule, we also have to add in the sum of an d epsilon n. So this second term here, an d epsilon n, this is the occupation numbers times the change in the energy levels. For our canonical ensemble, the volume doesn't change. And what that means, if the volume doesn't change, the energy can't change. Think of translational energy levels that are dependent on the volume. So if the energy levels themselves aren't changing, right? I mean, the energy doesn't change. Energy level 1 is always the same amount of joules or electron volts or whatever a unit is as it was before the change. This second term is 0, and the differential of energy is simply the energy level times the change in occupation. So we can have a changing of the levels that are occupied, but the values of the levels don't change themselves. From here, what we can do is, again, bringing in our canonical ensemble. Using our canonical ensemble, we can relate the energy change, right? What is the energy change? Well, this is internal energy we're talking about here because our volume isn't changing. And we know that the internal energy, so we can say dE equals du, that is equal to the reversible heat plus the reversible work, and the volume is constant, so the reversible work is equal to 0. So that means that this dE here is simply equal to the heat, and here we can bring in the thermodynamic definition of entropy. So entropy ds, the change in entropy, is equal to dq reversible over T, which in this case is simply equal to dE over T. So what that gets us is 1 over the temperature times the sum of epsilon n dAn. And we can use T, so using the relationship that 1 over kt is equal to beta, we can say that 1 over T is equal to k beta. So plugging that in here, we get k beta times the sum of epsilon n dAn. Next, we'll use the following relationship that we previously found in the Boltzmann distribution derivation. So in deriving the Boltzmann distribution, we had the following relationship. We said that the change in the natural log of the weight with respect to the occupation number plus our Lagrange multipliers here for particle number and energy, which was alpha minus beta epsilon n, was equal to 0. So what that means, we can rearrange this and have beta epsilon n being equal to the change in the natural log of the weight with respect to occupation number plus alpha. We can substitute this expression in here for beta times the sum of our epsilon n term. So what that gets us is that ds is equal to k times the sum of the derivative of the natural log of weight with respect to occupation number times the change in occupation numbers. And then we'll add in the second term, k times the sum of alpha times the change in occupation numbers. What we can do with this is look at the sum of the change in occupation numbers. So again, the change in occupation numbers is what's happening to the different energy levels, right? So how many particles are at energy level 0 compared to 1, compared to 2, compared to 3, and so on. If we're taking particles from somewhere, so if a particle was at level 0 and is now at level 1, dA0 is -1 and dA1 is +1, and they cancel out. So the sum of all of the change in occupation numbers has to be 0. So this term here becomes 0. For the first term, our dANs will cancel out, and we end with the relationship ds equals k times the sum over n of d natural log of w. There's no n dependence anymore. We've lost that. So we can say that ds is equal to k d natural log of w. And if we remove the differentials here, saying ds is equal to k times d natural log of w is the same as saying s is equal to k natural log of w. So this is how Boltzmann derives this equation. Now that we have this equation, how can we actually calculate entropy? That's going to be the next step. So the first thing to do is to plug in our definition for the weight. Now, for a molecular system, we can't really calculate the weight. The weight is going to be very complicated. So it's not even that it's just a large number, but it's simply we don't know the total number of energy levels, the percentage they're accessed. We can estimate these sorts of things, but we can't really calculate these infinite sorts of numbers. So what do we do? Well, we can say that the weight is equal to, and this is a thing that we should be familiar with by now, is equal to n factorial, the total number of molecules, divided by the product of all of the occupation numbers of all of the steps. So then we can plug this in, take the natural log of this, and we can say that the entropy is equal to k times the natural log of n factorial over pi a sub n factorial. We've handled this natural log before, so we can separate this up pretty easily into the following. So we can say that this is equal to k natural log of n factorial minus the sum of k times the natural log of a sub n factorial. And then with this, we go nk natural log of n minus nk. And then our sum terms here gets us minus k times the sum of an natural log of a sub n. And then we have plus k times the sum over n of a sub n. We've seen this before. The sum of our n's or a sub n's, right? This is just how many particles are there in every occupation number. That's simply the total number of particles. So this term here will cancel out with this term here. And that leaves us for our entropy as simply nk natural log of n minus k times the sum of an natural log of a sub n. Now, what we can do with this is actually bring this relationship back in and substitute that in for n. So what we get if we do this, we can pull out a k. So we can factor out a k, and this will give us k times what? Well, our n is simply the sum of all of the a sub n's. And then we have the natural log of n, and then we're subtracting here the sum of our a sub n's natural log of a sub n. We've seen this before, and for reasons that just make the math a little bit easier, we'll pull out a -1 here. So we'll say that this is equal to negative k times the sum of a sub n natural log of a sub n over n. So both of these terms have as sum over all our a sub n's, and then we use our log properties to get a sub n over n there. Now, why have we done this? Well, we've done this because what is a sub n over n? A sub n is the number of molecules existing at a certain energy level, and n is the total number of molecules. And what is that? It is simply the probability. So in this case, we can rewrite a sub n over n as the probability of our particles being at state n. And we consider the entropy is equal to negative k times the sum of a sub n natural log of p sub n. And we can do a little bit more rearranging here. If we don't know a sub n, that's okay, because we can factor out n and have negative nk times the sum of p sub n natural log of p sub n. So this here is what is called the probabilistic definition of entropy, based off of the probabilities of existing at a certain energy level. And we can use this along with the Boltzmann distribution to actually calculate the entropy for any state. Now we can push onward from here to actually get something based on Q, our microscopic partition function, by using Boltzmann's distribution. So Boltzmann's distribution, remember, says that P sub n, the probability of our particles being in a certain state, is simply equal to e to the minus beta epsilon n, so e raised to the negative energy over kT, divided by the partition function Q. So in our equation up here, we have the natural log of P sub n, which is then simply negative beta epsilon n minus the natural log of Q. So this is the route by which we are introducing the partition function Q into this definition of entropy. So we can go ahead and substitute in this term here and plug that in for the natural log of P sub n. So what that gets us is that the entropy then is going to be equal to negative k times the sum over a sub n times negative beta epsilon n minus the natural log of Q. So we can distribute this. This is going to give us k beta times the sum of a sub n epsilon n plus k times the sum of a sub n natural log of Q. Now we've seen these sorts of things before. So what is the sum of a sub n times the energy? Well, a sub n is the occupation level of every single energy level, and then E is the energy of that level. If we're summing over all of that, we have nothing less than the total energy of the system. So what this ends up being is simply the k beta times the energy of the system. And then for the second term, we simply have the sum of all of the occupation numbers, which is again the total number of particles in the system. So then we have plus kn natural log of Q, the partition function. We can relate k beta to temperature. We've done this before. So k beta is simply 1 over T. This gives us a definition of entropy as E over T, and then plus k natural log of Q raised to the n. Here we recognize that E is simply the internal energy U. So our entropy is U over T, and then Q to the n is the canonical partition function, capital Q. So our entropy can be written as U over T plus k natural log of Q, where Q is the canonical partition function. You may also see this written in a more compact form, where instead of saying this, we say it's equal to the derivative with respect to temperature of kT natural log of Q at constant volume. These are the same thing, and we'll usually rely on this expression here to actually solve problems. We can now apply this definition to actually calculate the entropies of ideal monatomic gases. We can do this for other gases as well, but the monatomic ones are just a little bit easier since they have a lot less going on. For a monatomic gas, the only degrees of freedom that are available are translational degrees of freedom. And that means that the internal energy U is simply equal to the translational internal energy. And the partition function Q is simply equal to the translational partition function, which is equal to volume over the thermal wavelength cubed. And this we can also write as 2 pi m kT raised to the 3/2 times the volume over Planck's constant Q. Maybe you remember that. With these definitions, we can actually now calculate the entropy. So the entropy is simply going to be for this ideal monatomic gas. The entropy is simply going to be the translational energy over T plus K natural log of Q to the N. And we introduce n factorial because for these particles, we can't tell the different monatomic gas atoms apart. So we have to divide by n factorial in this case. So what do we do? Well, we just evaluate this by plugging in our expressions from the top and using our log properties. So UT for translation, hopefully you remember, was simply 3/2 NKT. So plugging in 3/2 NKT for U, we end up with UT over T being 3/2 NK. And then we go ahead and evaluate this second term using our log properties. So we'll write for the first term, we will have NK natural log of Q, where Q is specifically our translational partition function. And then we'll have minus K times the natural log of N factorial. And we can use Stirling's approximation to say minus NK natural log of N, and then we'll have a plus NK. From here, we can evaluate this using the definition of the translational partition function. So first, we have 3/2 NK, and we have a single NK. We can group those together. 5/2 NK. And then we will have this term here becomes plus NK natural log of QT. Well, what's QT? In this case, it's the volume over the thermal wavelength cubed. And then we have minus NK natural log of N. From here, we can separate this out even further. We can say 5/2 NK plus NK natural log of V minus NK natural log of lambda cubed minus NK natural log of N. Here we can plug in what the thermal wavelength lambda is. And what that gets us, if we plug in that, we'll have our 5/2 NK plus NK natural log of the volume. And then we will have minus NK. Our thermal wavelength is h squared over 2 pi mkt to the 3/2. And then we have as minus NK natural log of N. What we're going to do here is group these two terms, but we're also going to pull out the temperature to see the temperature dependence of our entropy. So in doing that, what we end up with is, as always, our 5/2 NK. We have plus NK natural log of V. Here we have now minus 3/2 NK natural log of T. And then the last term where we bring in our N, we have minus NK. And here to put our N in this 3/2 with us, we'll put N to the 2/3, which is a little bit wonky, but there it goes. So N to the 2/3 h squared over 2 pi mk raised to the 3/2. And so in this case, we have our almost complete equation. What we're going to do now is turn this into molar units, because that's typically how we think about these properties like entropy. So to do that, we're going to divide, we're going to convert NK, the number of particles times Boltzmann's constant, into NR, the number of moles of particles times the gas constant. So here we have 5/2 NR plus NR natural log of V minus 3/2 NR natural log of T minus NR. And what we have here in this expression now, to get rid of N, the number of particles, we can do that by simply having N, the number of moles, times Avogadro's number is equal to the number of particles. So N times Avogadro's number raised to the 2/3, and then we'll still have h squared over 2 pi mk to 3/2. And with this expression, if we know the volume and temperature and the number of moles, we can figure out what the entropy for an ideal monatomic gas should actually be. These terms are pooled together into what's called the Sacker-Tetrode equation, which combines all of these logarithms. And what that gives us is that the entropy of an ideal monatomic gas is equal to the number of moles of gas times the gas constant times the natural log of e to the 5/2 times the volume over the thermal wavelength cubed of the particle times the number of particles. And what we do to get around these sorts of things, like the number of particles and the volume that might not be known, to convert to ideal equations or situations, we use the pressure. So we have nr times the natural log of RT e to the 5/2 over the thermal wavelength cubed times Avogadro's number times the pressure. In this equation, the e to the 5/2 comes from this term, putting that into the natural logarithm. So the e is the number e, 2.718, and it goes on from there, not the fundamental charge of the electron. This equation is based off of statistical mechanics, and it reproduces our classical understanding of entropy. For example, consider an isothermal expansion. So we want to calculate a change in entropy with constant temperature. How does entropy change? Well, looking at our equation, we have 4 terms. We have our first term, second term, third term, and fourth term. The first term is 5/2 nr, only constants. The fourth term is a whole mess that's also made up of constants for specific molecules. So everything in here is a fundamental constant except for the number of particles, which would be constant under an isothermal condition, and the mass, which is also constant. The third term is temperature dependent. So if that's constant, that's not changing. And all we have is the second term. So if we have an isothermal process, the only thing that could possibly change in this entropy equation is this second term here. So a change in entropy then would be S final minus S initial, which would be nr natural log of V final minus nr natural log of V initial, which would be nr times the natural log of V final over V initial. And this is the equation that we use using classical bulk thermodynamics to describe changes in entropy for isothermal processes for an ideal monatomic gas. And so again, this is pretty remarkable that we can actually do this. We can explain thermodynamics simply using quantum mechanics, or maybe not simply, but using nothing except for first principles here in quantum mechanics, which are things like the mass of the particles, the energy level spacings of the particles, and so forth. This approach also provides some interesting insights into entropy. We see how entropy varies based off of volume and temperature, which we could calculate with classical thermodynamics. However, we have these other 2 terms, the first and the fourth term, that are constants. So if all we can measure classically is a change in entropy, we can't actually measure these, and we can only see that they exist when we bring in quantum mechanics. So we couldn't identify the presence of these terms doing simple change in entropy calculations, but we can see that they are here for different particles. And again, this is pretty accurate. So if we want to do some comparisons, in theory, according to this theory, if we plug in numbers for neon, we predict an entropy for neon at room temperature of 146 joules per mole Kelvin. For krypton, we get 164. The experimentally measured values for these things are 146.48 and 163.89. So this isn't an example of our theory being like kind of good. Our theory here is spot on and basically exactly predicts the entropy of these sorts of things. We can also predict the entropy for more complicated molecules if we want. There's a little bit more math because the internal energy as well as the partition function are a little bit more complicated for other things. Now, this doesn't quite work for every single molecule. And there are some molecules where there is a little bit of a fail. And the example for that we're going to look at here is carbon monoxide. So carbon monoxide has a pretty big failure compared to either neon and krypton. So neon and krypton are basically spot on for their theoretical entropies. But here, carbon monoxide is about 5 joules per mole Kelvin higher. So what causes this? Is our theory failing? The cause of this is what's known as residual entropy, as you can see by the title here. So what is residual entropy? Well, residual entropy is entropy that is present at low temperatures due to essentially orientational differences. So if you recall, we have entropy being 0 at 0 Kelvin. We get this from our third law of thermodynamics that says the entropy of a pure crystalline solid is 0 at 0 Kelvin. So this goes without saying, but if we do not have a pure crystalline solid, we will not have zero entropy at 0 Kelvin. Now, what do we have? So how could we have a non-pure crystalline solid at 0 Kelvin? Carbon monoxide gives us an example of this. So carbon monoxide, if you were to go back, and I had my Chem 101 students do this, we draw Lewis structures of this. Carbon monoxide has a dipole from carbon and oxygen, but that dipole is opposed by the formal charges on the carbon and the oxygen. So that means that carbon monoxide is actually not very polar, which is why our bodies mistake it for oxygen and it suffocates us if we breathe it in. So what this means is that at 0 Kelvin, there's not a super strong orientational preference of this molecule. And so we don't actually have a pure crystalline solid. We could, for example, flip this guy in the middle into the opposite orientation. So we can have a different orientation of this molecule. Now, what does that do? Well, why is the entropy 0 at 0 Kelvin? It's not just a magical third law of thermodynamics, but it's because the weight, if you have no motion and only one orientation, is 1. And so the natural log of 1 is 0, so the entropy is 0. If you don't have that, if you have different possible configurations, your entropy is not 0. And we can actually calculate what the entropy is. So the entropy would simply be equal to K natural log of W. And for carbon monoxide here, there would be 2 possible orientations for every molecule. It could be facing to the right or to the left. And so our weight is now 2 raised to the n. So K natural log of 2 to the n becomes NK natural log of 2, which we can convert to NR natural log of 2, which is 5.76 joules per mole Kelvin. And that is about enough to account for the difference between the theoretical and the experimentally measured entropies. Now, these aren't quite the same, and I would imagine that's because there is some partial selectivity here. So this is not exactly what the entropy would be, because there is some slight orientational preference, but not enough to get an actual pure crystalline solid. Now that we have entropy pretty well settled, we'll go through our other thermodynamic functions pretty quickly here based off of internal energy and entropy. So we'll start at an odd place, perhaps. We'll start with the Helmholtz energy. And that's because the Helmholtz energy, if you remember, is based off of the internal energy and the entropy. And these are the 2 equations we spent a lot of time solving for. So the Helmholtz energy is simply the internal energy minus T times the entropy. In this case, that is U minus T. And what's the entropy? Well, the entropy we just described as U over T plus K natural log of the canonical partition function Q. So that's going to give us U minus KT natural log of Q. The U's will cancel, and we'll simply get negative KT natural log of Q. This is our definition of the Helmholtz energy. With this, we can actually do a pretty interesting thing. So going back to our Maxwell relations, we had the following result. We had that the pressure was equal to the negative partial derivative of the Helmholtz free energy with respect to volume at constant temperature. Why is this interesting? Well, let's do something here for a monatomic gas. Let's actually evaluate this. So here we're saying that this is equal to the negative partial derivative with respect to volume of negative KT natural log of Q at constant temperature. So we can pull out the KT here. This gives us KT times the derivative with respect to volume of the natural log of Q. What is the natural log of Q? Well, that's simply, we've done this many times now, that's simply equal to the natural log of Q to the n over n factorial if what we're dealing with is a monatomic gas. We only have to use the translational partition function here. So we've done this derivative a few times now. We can say that it's simply equal to kT times the derivative of the volume. We get our n from our natural log of q to the n, and the natural log of n factorial is going to end up canceling out since it is in fact a constant. So we can use our derivatives here. Our q for translation is simply equal to the volume over the thermal wavelength cubed. So now we're taking the derivative with respect to volume of the natural log of the volume over the thermal wavelength cubed. That's going to give us simply 1 over v, like we've seen before. So here we'll have nkt over v, and I think now you'll be able to see what we're doing here. So we've made this substitution a good number of times now, but nk is simply lowercase nr, and what we have is p is equal to nRT over v, which is the ideal gas law. So this is a remarkable feat because we've predicted the ideal gas law using no experimental observation. So for a monatomic gas, using nothing other than quantum mechanics, we predict that the pressure of that gas is equal to the number of moles times the gas constant times the temperature divided by the volume. So again, this shows the power of this statistical thermodynamics approach. Moving on from the Helmholtz energy, we'll do enthalpy. The enthalpy ends up being a bit nasty. So our enthalpy was originally defined as the internal energy plus PV. And we'll use this definition of P that we have above for the enthalpy. So we'll say that this is equal to U. And remember, U we defined as the negative derivative with respect to beta of the natural log of Q at constant volume. So this is how we calculated Q or U based on statistical thermodynamics. And then P we just have here. P is equal to the negative derivative of the Helmholtz free energy with respect to volume. And we can plug in what the Helmholtz free energy is here. I'm going to skip a few steps and simply say that the enthalpy is equal to the temperature times kT times the derivative with respect to temperature of the natural log of Q at constant volume plus Vk times the derivative with respect to volume of the natural log of Q at constant temperature. So this is our definition of enthalpy. Again, it's a little nasty, but we can use it to calculate the enthalpy based off of quantum mechanics if we want. We can do a similar thing for the Gibbs free energy. Our Gibbs free energy is, of course, the enthalpy minus the temperature times the entropy, but we don't have to go to this nasty enthalpy equation. What we can do is substitute in for HU plus PV. So this gives us U plus PV minus TS, and U minus TS is the Helmholtz energy. So the Gibbs free energy is also equal to the Helmholtz energy plus PV. Again, doing the same sort of thing and skipping a little bit of work here, we can say that the Gibbs free energy is equal to negative kT times the natural log of Q minus the volume times the derivative with respect to volume of the natural log of Q at constant temperature. We could use a different way to go about this, incorporating the ideal gas law. So we could, instead of this, we could say, well, I know that PV is equal to nRT or nKT. So why don't I just bring that in? And so we will. So we'll try that and see what that gets us. We'll say that the Gibbs free energy is equal to the Helmholtz energy plus PV. In this case, we'll use the definition of Helmholtz free energy as negative kT natural log of Q. And then we'll add in nKT for PV. We can group this together, and so what we can have is we can have negative kT natural log of Q to the n over n factorial plus nkt. And then we can use our log properties and say that this is equal to negative nkt natural log of q plus nkt natural log of n minus nkt. And then we have, so this is using Stirling's approximation on the first term. And then our second term here is plus nkt. So we can cancel out these two terms here. Then we can group these two guys back together to say that g is equal to negative nkt natural log of q over n, or of course negative nrt natural log of q over n. And this expression here of what the Gibbs free energy is a little bit more useful and intuitive than this a little bit more gross one up here. So at constant temperature, the only difference between two states, right, if you have state 1 and state 2, is the partition function. The more positive the partition function, the more negative the Gibbs free energy. Since the partition function is a measure of how many states are accessible to a molecule, the lowest free energy state will be the one that has the most energy states accessible. So this kind of relates quantum mechanics to our understanding of why things are spontaneous. Finally, here we'll derive our equilibrium constant. And again, to put all of this kind of math we've been doing back into context, if we can formulate an equation for the equilibrium constant, we'll be able to describe why some chemicals are more favorable than others and what drives them to get to products instead of reactants. So like we often do when talking about equilibrium, we'll consider our classic arbitrary reaction of A molecules of A plus B molecules of B reacting in equilibrium to make C molecules of C and D molecules of D. What's the free energy of this process? We're very comfortable with this. The free energy for this process is the sum of all of the free energies of our products minus reactants. This is our new coefficients times our reactants and our products. And so we can write this out as follows. We can say that the change in Gibbs free energy for this reaction is simply equal to the number of moles of C times the molar Gibbs free energy of C, plus the number of moles of D times the molar Gibbs free energy of D, minus the number of moles of A times the molar Gibbs free energy of A, and the number of moles of B times the molar Gibbs free energy of B. Now, what we're going to do here is bring in our definitions for what the Gibbs free energy is that we just described. So for every term here, we'll go ahead and grab this guy and plug it in for the molar Gibbs free energy. Now, if we have a molar Gibbs free energy, n, lowercase n is equal to 1. We have 1 mole. The uppercase n is in fact equal to Avogadro's number because we have 1 mole of particles, so we have Avogadro's number of particles. So this gives us that the change in free energy is going to be equal to negative CRT natural log of Q over QC over Avogadro's number minus DRT natural log QD over Avogadro's number plus ART natural log of Q sub A over Avogadro's number plus BRT natural log of Q sub B over Avogadro's number. Here I can group all of these together into the following expression. I can say this is equal to negative RT times the natural log of QC over Avogadro's number raised to the C times QD over Avogadro times QB over Avogadro's number raised to the B. And all of these terms are in natural log. Now, what have I done? Well, we know, and we're very familiar at this point, that delta G naught for a reaction is simply equal to negative RT natural log of the equilibrium constant. So if I have delta G being equal to RT times this natural log of this mess based on the partition functions, those are the same thing. And I can say that Kp is equal to, I'm just going to copy all this stuff out here. It's equal to all of these terms here based off of the partition functions. So the equilibrium constant is as follows here. We need one more modification, and that's because we have removed the 0 point energy. So remember, we took the 0 point energy out of bond vibrations because we were only comparing those bond vibrations relative to each other, and it didn't matter if we started at the 0 point energy or at 0. If we're talking about differences between molecules, now all of a sudden those are important. We can't just ignore the 0 point energy. So we have to put the 0 point energy back in. Well, how do we do that? Well, it's pretty easy, actually. So the 0 point energy, right, what we did is we took it out of the vibrational partition function. So the vibrational partition function that we have been using, which we can call Q vibration prime, is equal to the actual vibrational partition function, but we've taken out the 0 point energy. And remember, these 0 point energies were participating in every single term. So what we can do is multiply by e to the beta epsilon, where epsilon is the difference between the actual ground state and this artificial 0 that we described. So that's the 0 point energy. And if we add that back in, we do it for every single term. So to add these into our expression, QC becomes e to the beta epsilon c QC. And this is raised to the c in the equation up here. So we have the following. We have 4 more terms that are going to come in. It's going to be e to the beta epsilon c raised to the c times e to the beta epsilon d raised to the d over e to the beta epsilon a raised to the a and e to the beta epsilon b raised to the b. Now, using our exponents, our exponential properties, what we'll get is this is the same as e, and every term has a beta in it, so we can put a beta here, to the beta times c epsilon c plus d epsilon d minus a epsilon a minus b epsilon b. And we can put all of that back in together, and we'll shorten the notation and say that this is equal to e to the minus beta delta epsilon. So plugging that back in here, we need to have this e to the minus beta delta epsilon term that talks about the differences in the actual ground states for the vibrational energy levels for all of these molecules. And this gives us our actual equilibrium constant. Here we can see there are 2 factors for what will drive a reaction towards equilibrium. If the products have more energy levels available than the reactants, that means that QC and QD are greater than QA and QB, and that will drive the reaction forward. It'll be favorable to occupy more of these states. However, we have this delta epsilon here, and this will favor the lowest 0 point energy. So in this case, in this simple process here, the products have a higher 0 point energy than the ground states. This actually favors the reactants and makes it more likely that the reactants will be more stable than the products. So we can see that equilibrium favors 2 things. It favors a lower 0 point energy, and it also favors closer spaced energy levels for the reactants, or for the dominant species. And so putting these things together, we could actually go and calculate equilibrium constants based on nothing other than quantum mechanics to see if 2 reactants or products or what have you would be expected to be more favorable under which conditions. And we can understand why that is. We don't just have to say, well, that is what's observed. We can understand that, actually. So that's all we have here for statistical thermodynamics. And our conclusions are pretty straightforward. We've been talking about these ideas for a while, and we finally had the chance to put them all together. The thermodynamic functions that we know and love are all based off of quantum mechanics. And we can use statistics and quantum mechanics to put these together and actually calculate very, very, very accurate thermodynamic functions without considering the bulk properties. So we only have to know how monatomic gases behave, and we can predict the ideal gas law and so forth. So this is a very powerful technique, a very accurate technique that gives us a large degree of understanding into the way in which chemistry fundamentally works.